All right, so let's take a look at question 26 from the Advanced Maths 2024 paper. This is also question 41 in the Standard 2 paper. So we are told 25 years ago, Phoenix deposited a sum of money into a new bank account earning 2.4% interest per annum compound monthly. We're given a present value table of value. So this is how much you'd need to deposit at the start in order to get a $1 payment per period for the number of periods with the given interest rates. We are told he does $2,000, so $2,000 per month for the first 15 years, which is 180 months. And then he does 1,200 a month for the next 10 years. 10 years, which is 120 months. We're told the interest rate is 2.4% per annum, which equates to 0.2% per month. So let's draw a little financial line and think about this. We have a little financial line. So the majority of the withdrawals are $2,000 withdrawals. So they happen, this is where he deposits the money, then he gets the 2,000 and so on. After all of the $2,000 withdrawals, there are 180 of those withdrawals. He then starts withdrawing 1,200. So it reduces from 2,000 to 1,200, and then he has 120 of these, and then there is nothing left in the account at the end. So we could think of this as two separate lots of withdrawals. If we think about the first 180, these are the $2,000 withdrawals. We can use the table straight away to work out how much he needs to deposit to get $182,000 withdrawals. So 180, we look for the period 180, interest rates 0.2%, so that's 0.002, 180, 0.002, that's 151.036. That's how much you'd need to deposit to get $181 withdrawals. Multiply that by 2,000, and that will give us 151.036 times 2,000 is 302072. Now, the last 120 payments are not included in this. So we're going to think about them separately. When we did the $2,000 repayments, we thought of their terms in terms of the past value, right? How much on day one did you have to deposit? For the 1200s, we're going to calculate them from the end of the 2000 payments. How much would you have to have in the account remaining at the end of the $2,000 withdrawals to get 120 $1,200 withdrawals? So 120, 0.02, that's 106.592. Multiply that by 1200. We get 106.592 times 1200. Calculator tells me this is 127,910.40. But this is at, let's call this period alpha, right? This is the amount you'd need in the account at time alpha, not the amount you'd need at time 0 at the beginning. So we need to adjust that using the compound interest formula, because the first 15 years that money is sitting in the account for the last payments, it's not going to be used. It's just going to sit there and it's going to accrue compound interest. So we need to scale it back so that it's in terms of the 0 time period terms. So A equals P times 1 plus R to the N. This implies that P is equal to A on 1 plus R to the N. So we have the amount you need at time 0, this 127,000, the amount that has to go in to become that with compound interest, is 127,910.40 divided by bracket 1.002 to the power of 180. because there's 180 compounding periods for this. So this is equal to 127. Let's put this in our calculator. 127910.40 over 1.002 to the power of 180. Calculator tells me this is 89,272.15 to two decimal places. So the amount you need to put in initially is the sum of the 89,000 and the 300. So the total needed on day one is 302,072 plus 89272.15. So this is 302,072 plus 89272.15. My calculator tells me this is 391,344.15. So this is approximately the amount that you'd need to put in the account in order to end up with $182,000 withdrawals and then 120 $1,200 withdrawals. Now, this, because of the way this question works, there's a few different ways that you can calculate this. And depending on how you calculate it and what assumptions you make in terms of the question itself, will depend what answers you get. So your answers can be up or down a little bit. The NESA does a very shorthand version of this same example where their 15-year extra total ends up different by about 65 cents from this answer. These are relatively minor discrepancies, and they're just going to happen when you're using different answers. It's to do with how many compounding periods you count, which methods of formulation you're using, what rounding is built into which of the calculations, and all of that. So if you use a different method to this, you might be up or down by a little bit. It doesn't really matter if you're off by a tiny little bit. If you're using a different method where that is associated with the method, it's still technically the correct value. So this is question 26.